Hey everyone, welcome back to PACELC. In this video, we're going to speed run some must-know system performance strategies using this one diagram as our map. Think about this as your mental checklist when you're designing large-scale backends or AI platforms. CAP, PACELC, Sharding, caching, consistent hashing, and async processing. These are the levers you keep pulling again and again when systems start to fall over under real traffic. Let's start with the CAP theorem in the top left. CAP says that in a distributed system facing a network partition, you must choose between consistency and availability. You can't have all three. Consistency, availability, and partition tolerance. Partition tolerance is non-negotiable in real networks, so every system leans either more CP or more AP under failure. A CP system will sacrifice availability to keep data correct, while an AP system will keep taking requests even if some reads are slightly stale. Next to that is PACELC, which extends CAP to normal conditions. It says, if there is a partition, P, you trade availability, A versus consistency, C. Else, E. When the network is healthy, you usually trade latency, L, versus consistency, C. That's why some databases give you tunable consistency levels. You can dial in more latency for stronger guarantees, or relax consistency for faster responses. In practice, PACELC explains why eventual consistency, or read replicas, exist as performance tools, not just academic concepts. Moving to the middle row, database Sharding. Sharding is about splitting your data across multiple physical databases based on a key, so each node holds only a subset of the total data. A hash function takes the key and decides which shard it belongs to. This lets you scale out horizontally instead of trying to run everything on a single monster database instance. Of course, once you shard, you now have to think about cross-shard queries, resharding when you add capacity, and making sure your shard key doesn't create hotspots. On the right, we have database caching. Caching is often your first lever when performance is bad. Put a fast key value store like Redis or Memcached in front of a slower database. On a read path, the app checks the cache first. If it's a miss, it fetches from the DB, then writes the result back into the cache. On write paths, you either update the DB, then invalidate or update the cache. The tricky part is cache invalidation and choosing TTLs so you don't serve stale data forever while still getting the performance boost. Bottom left. Finally, asynchronous processing on the bottom right. Not every request needs to wait for a long-running task to finish. With async, service A places a message onto a broker or queue, and service B processes it in the background. The user gets a quick acknowledgement instead of staring at a spinning loader.